this is a work, first of all, that is being done in collaboration with Ana Martins and João Lagarto. They are from ISEL, and João in particular works in the energy field, and I was challenged to do something with them in this field, also in this domain. So this combined distance between time series is going to be applied in this particular domain. So an agenda, a brief introduction, then what's the combined distance between time series, then what's the performance of this measure when compared with others, and finally, two applications. One referred to clustering of time series of day-ahead electricity market prices of European countries, and the second one referring to discover patterns of electricity consumption in Portugal. Discussion and perspectives, and the talk. So first of all, we know that the dissimilarity measures which are used in clustering or some more simple tasks such as querying, database, or also classification, they can be critical in these tasks. And we recently proposed a new dissimilarity measure, which is a convex combination for normalized distance measures. And this idea was to integrate the several aspects of the differences between the time series, capturing differences in scale, differences in trends, and also differences that express the dissimilarity between frequencies or cyclical components, and also comparing the series in terms of their dependence on past observations. First of all, I'm going to present an experimental analysis to evaluate the competitive performance of this measure. And I will resort to the data sets that are originated in the University of California Riverside archive. This is a very large collection of data sets. They are labeled, and we have data for training and data for test. And the clustering applications using this COMB measure will be referred to 2018 data, the first one, which regards the patterns of day-ahead electricity prices in the European regions. And the second one tries to review electricity consumption patterns concerning Portugal between 2014 and 2019. The distance, it was proposed some time ago, although published more recently. And this is, as I said, a convex combination of Euclidean, Pearson-based distance, which is not, of course, exactly the Pearson correlation. It is based on this measure here, and the periodogram-based measure, as well as the autocorrelation-based measure. And in our work, most of it will be using a uniform convex combination, meaning that all these distances will be considered with uniform weights. Let's just give you an example of two series which are very apart from the Euclidean distance point of view, but they are similar from the Pearson distance point of view. And these are similar from both points of view. For these two series, which this one is very different from this one in what refers to cyclical patterns, which are illustrated with the help of the periodogram here. So in periods of 12, 24 hours, and 36, and so on, we register some peaks. And these cyclical patterns, they are captured with the help of the periodogram, and the distance, Euclidean distance between periodograms will be a component of our combined distance. Also, the distance which takes into account the dependence of previous observations, which is common in time series, is considered here. For instance, this peak here can be seen as dependent on this one, and so on, with 4 period interval or lag, and with a negative correlation with this one, which also repeats itself. So we try to capture the differences in series, which can be several. In order to compare this distance with other that are commonly used, we refer to some baseline distances which are used commonly in several studies, such as the Euclidean distance that cannot be avoided, not just because it is very well known, but despite its simplicity, it is in general very effective. The dynamic time warping, which is a winner in most studies or variants of this distance, and the complexity invariance distance, which is kind of a new distance in what refers to these comparison studies. The data sets we are using to compare these distances, they are referred to several domains, and they have several dimensions: training, test, and length. And we limited the number of data sets due to computational cost and considered 57. And they were, after this, divided into data sets with 2 and more classes. They are quite balanced in this way. So we follow this methodology, which is used in previous studies to compare the distances, meaning we use the one nearest neighbor classifier on label data to evaluate the comparative performance of these 4 distances. And we know that the distance measure, which is used in one nearest neighbor, it is critical in the performance of this classifier. So the accuracy of the final classification could be a good indicator of the performance of this measure. In fact, according to Ding et al., and it was cited in Paparizos in a more recent paper, these one nearest neighbor classifiers are suitable methods for distance measure evaluation for several reasons. And of course, the more critical one is that they are dependent on the choice of the distance measure, and also they are very easy to implement. So we follow this methodology. Just a quick view about the dynamic time warping distance, which I said is in fact very well known, and it is commonly a winner in comparative studies. So the idea is to align the 2 series in order to obtain the distance between them. So we do not think that the first period it is aligned with the first of the other series. Maybe it is not. So the correspondence, the better correspondence or optimal correspondence or alignment can be found, and that's the idea of the DTW distance. Of course, this alignment or matching has some rules, and also in general, not all the series is considered for the matching, but a window, just like 20% of the data of the series is used. The complexity invariant distance, it is a distance proposed by Batista and al. And it is in a very intuitive way that we measure the distance between time series. The idea is if a series is more complex, like this one, when we stretch the series, we will have a length that is above the values of the other ones. So this is the idea of the complexity factor, and this complexity factor, it's used as a factor in Euclidean distance, with Euclidean distance. So the 57 UCR data sets, which are here, this is, of course, as I said before, we try to balance the data sets in resorting to different types, one with 2 classes and the other with more than 2 classes, wondering if the distances may perform differently between these 2 types of data sets. So in order to compare the classifier results, instead of using accuracy, we used Uberty index, which can be viewed as a corrected accuracy. So we see accuracy here, the percentage of correct classifications, but this is corrected by the percentage of the model class, which is seen as the default predictive ability. Let's say if we have 90% in this model class, having an accuracy of 90%, we'll have just the 0 Uberty index result. And if the accuracy is below this model class percentage, it will be below 0. So after seeing the Uberty index, we can see more than after seeing the results of accuracy, which doesn't take into account the prevalence of the model class. The comparative performance of this COM measure, this is the results that refer to the 57 data sets. And we can see here that the DTW has the highest mean, and it performs well, as it has also the highest 50 percentile, the median. And this is the second place for the proposed distance. And in what regards the comparative performance from an inferential point of view, resorting to the Friedman's test, we can see that for k equals to 2, we have no differences that are significant, but with k above 2, we have significant differences, but they are all rooted in the difference between the performance of Euclidean and DTW. In what regards the sample results, the proposed distance, it surpasses slightly the performance of all the competitors, including the DTW. In what refers to the computation time, which is the reverse of the experiment, not only the performance, but how much time we have to conduct the analysis. So in here we see that the loser is the DTW, which was the winner before, and the proposed distance stays in second place also. So it is the second best in what regards the performance, the second worst in what regards the time of computation, but it has a significant difference between the time of computation of the DTW and of the proposed distance. So it is a significant difference between these, And it was very apparent in the previous slide how much more time we need to compute this DTW when compared to all other distances. So for the comparison between the distances, we also wanted to understand what's happening with these examples where our distance wins and where our distance loses. For instance, the comp distance wins when we refer to this particular data set, which it was originated in the CMU Graphics Lab motion capture data, referring to right to movements, and the classes are walk normally and walk abnormally. And according to the Uberty index, we have much better results for the classifier when using the comp distance. The comp distance loses in a very difficult scenario for all distances because the classes are very ill separated, but it is the worst result. So we wanted to explore these scenarios, and one thing we tried was to understand them a little better. So the nodoids of these classes of the toe segmentation example, they differ, of course, when referring to the complexity invariance distance. Remember, this is very different time series from this one, which is much more simple according to this criterion. According to the DTW criterion, you can see that the nodoids are in fact different, but not apparently not as different as in here. And one thing we could see here is that we don't only see nodoids that differ in the what refers to the scale, but also to the tendency. So this is one of the characteristics of the proposed distance. It captures all kinds of differences between the time series. And when referring to this ill-separated classes example, the herring example, we can see that the nodoids are very similar. The nodoids, in fact, those that are recovered by these three distances are exactly the same. And we wanted to see the potential improvement of our proposed distance by using different weights. So in here, we tried changing the weights, and after changing the weights, we obtained a positive Uberty index. And if you remember, a negative Uberty index was obtained for all the competitors. So it is possible to improve this worst result and to transform it in the best results. After these experiments, and the chronology is not exactly this one because we started first specifically with this example of clustering. And this was our motivation for obtaining the COM measure. So we were dealing with the head electricity market prices in European countries. And we know that in the future, the electricity market, the European electricity market should be integrated. And we hope that happens because we can all gain. The costs will be lower and everybody will have the interconnections necessary to obtain electricity from more sustainable sources. And so we try to understand the still heterogeneous markets, electricity markets. So we see here that the electricity markets under study are the Nibel, the Italian, the Nord Pool, the French, and the German markets. And we study 26 regions of these markets, and data of 2018 is considered. So we resort, of course, to a clustering algorithm to understand the patterns of the different patterns of electricity prices. Just a quick view on the markets which are being considered. As we see here, the Nord Pool market, it consists of 16 price areas. The Portugal and Spain, they form the Nibel markets, and then Italy, one country, several regions, and Germany and France, one country, one region. The day-ahead prices, market prices, they are obtained by this encounter with between the demand and the supply. So we have here the power producers offer the electricity, and we have here the demand, and they can see the intersection of demand and supply, and this gives the market price of the energy. So this market works in a 24-hour basis. And of course, these prices vary since, of course, consumption and production also are not constant during the day. In order to obtain the clusters, the K-Medoids algorithm was used for clustering. It generalizes the k-means. It can use arbitrarily defined distance measures. It aims at the minimization of the distance of objects belonging to a cluster from the cluster medoid, instead of a cluster centroid, like in k-means, which means we would have to calculate the average between time series, which is tricky. And it is somewhat more flexible in terms of cluster shapes and more robust to outliers and noise than k-means is. In what concerns time series clustering, the fact, as I said, that a medoid is a member of the data set instead of an average of several time series is a clear advantage. And in order to decide on the number of clusters, we use several cohesion separation indices, and we used a summarized measure of all these indices. For instance, for this application, referring to the day-ahead prices in the market, if we were to use the Euclidean-based clustering results, 2 clusters would be constituted. And 2, since the normalized sum, the sum of normalized indices indicates this value. This is, of course, the reverse of the silhouette after normalization, because in fact we tried also an MDU representation, which is not present here. So this is normalization that reverses the indicator. In this MDS map, we can see that Sicily, it clearly stays in this cluster, but despite that, it is not as homogeneous, of course, as this group here. So it ends up being not connected to the mainland of Italy all the time. So due to interconnection congestion, different prices may arise. That difference it is between Sicily and the other Italian regions is not apparent in these clustering results that were derived on the distance based on Pearson correlation. So in fact, we see that here that considering this distance, the linear increasing and decreasing patterns are being considered. And so we just find these two main clusters, one that is separating what we call the North Pole market and the other markets apart. So prices tendencies to increase and decrease are very different for these two clusters. Considering the cyclical patterns, we end up with 4 clusters. Sicily now is a single cluster, and Latvia and Lithuania constitute also an isolated cluster. So we know that they have reduced renewable production, which combined with the low capacity of interconnection with Estonia, which is nearby, it may originate an increase in price variation between the off-peak and peak hours, which can justify this output. Finally, this is, of course, the periodograms which are pictured here. And we can see, for instance, the Sicily here with a different pattern from the other ones. And of course, we have the patterns also for Latvia and Lithuania, which are different. Now, using the autocorrelation based clustering results, the results obtained yields 3 clusters, and we cannot see any related geography in these clusters. So Mibel stays with some regions of Norway and Sweden, and so Portugal and Spain are considered here in this cluster with North Pole regions, which is of course not a geographic proximity justifying this, and so on. So we have also some regions of Italy, Sweden, and Denmark staying together. These are the correlograms, and we have the differences between the clusters. Clusters are indicated with different colors as the periodograms before. So these differences justify, for instance, the autocorrelation structure of Sicily. It can be seen that it differs from the other ones, for example. When using the comp measure-based results, we end up with these clusters. These 6 clusters, they have a geographical coherence, and it was very interesting to see them emerge from our combined distance. So they reflect, these clusters, not only different price patterns, but also geographic proximity, which of course may underlie the patterns. And understanding the clusters a little better, we can see that Sweden, with exception of this region here, which is in the south, and Norway are geographically close and produce low-cost technology energy. So that's why they are together. Finland and the Baltic countries are geographically close. They use fossil energy, and although Finland has a lot of nuclear also. And Denmark, Germany, and also Sweden, this region in the south, they are together. So this difference from this region from the other ones in Sweden, it is because Malmö is a very industrialized area in the south and very close to Denmark. So in order to satisfy all the demand in this area, it is used, they use the Danish production, the energy produced in Denmark. Sicily, it has a different pattern. A lot of wind, but variety variability of the wind is very high. So when it has to resort to the mainland energy and import electricity from mainland Italy, the prices can be very, very different. And of course, it is also limited by the interconnection capacity with the mainland. The cluster joining mainland with France, it was somewhat unexpected for our colleague João Lagarto. And since France has much of its electricity production from nuclear power plants, which in terms of the cost structure could be closer to Spain than Italy. Nevertheless, we could also consider that the electricity grid interconnection between Spain and France is very different from the one connecting France and Italy, and it could justify this clustering. Finally, the grouping of Portugal and Spain is quite natural, grounded in geography and the interconnection capacity, and in electricity production from the same type of technologies. The major renewable production, hydro, wind, and solar in the case of Spain, and also coal and natural gas. So in this application, we conclude that the K-methods allow to overcome the limitations of K-means. Of course, it enabled us to use our proposed distance. The alternative distance measure were not able to capture all the differences between the time series, and the clusters obtained could be useful in future electricity price forecasts. As to daily patterns of electricity consumption in Portugal, the second application, we have the goal of the present work is to obtain clusters of electricity consumption time series, and this data refers to the Portuguese transmission system operator and to the period that goes from 2014 to 2019. We ended up using K-methods and combined distance also, but in the process of building the cluster, we learned that a semi-hierarchical clustering procedure could obtain better results than the simple K-methods. So the proposed approach is first, of course, we calculate the distance between the time series. Then we run the K-methods with a number of clusters from 1 to 20. Then we calculate the silhouette index values and decide on the K. And we repeat these steps and within the clusters obtained in the previous step, just constrained by the fact that a clustering structure should emerge. So we point this constraint as a silhouette being above 0.2. Of course, results should also be interesting from the application point of view. So first, we use K-methods and obtain these two clusters. We used as a criterion to determine the number of clusters, this time only the silhouette, which is coherent with the stop rule, stopping rule based on the silhouette. So we first capture the differences between loads on non-working days and loads on working days. On the second, then we proceed, we cluster these elements and separately we cluster also these. So we end up discovering the days of different seasons. So we were able to capture the autumn and winter period and the spring and summer period. And for instance, for the non-working days, we can see they were divided in these two different subclusters. And The one that is the highest consumption, it is described here in more details. So it is, of course, non-working days, and this is the majority are Monday to Friday days, while some of the Saturday, Sunday, and holiday periods are in these non-working days. Finally, the level 2, we divided the loads of non-working days between autumn and winter, and spring and summer. And this division here, it is apparent also in the days, how they are separated in these two clusters. So the highest consumption refers to these more winter days. So these winter months from October, mostly from November to February. And the spring and summer days, of course, the concentration is different. And finally, we discover differences between the daily loads that were not captured by the experts, because we could argue that an expert would divide loads from non-working and working days and also consider the different seasons. But then the division of these subclusters, it can be further detailed, and we obtained these clusters here. And this is the more heterogeneous one, the one referring to spring and summer period and non-working days. And we believe these are the most difficult days to predict the electricity load. These are the silhouette indices corresponding to this clustering, to this one, and that one. As I said before, they are above 0.2, which was a constraint of our approach. So a little more comments on these clusters. So C11, the first cluster, autumn and winter, Saturdays and special non-working days, as we called it. Then, for instance, in this cluster, all Christmas Day were captured, and this cluster captures Saturdays and Sundays, so weekends, but they refer to March and highest consumption, while, for instance, here we capture Saturdays, Sundays, and holidays from April to July. So we have different patterns according not only to the days of the week, but also, of course, to the months of the year. And referring to working days, there are differences here from October to December, so referring to the end of the year. And between November and February, we find higher consumption when compared to the previous cluster. And when days get bigger, we have lower consumption. And for instance, this cluster has higher consumption when compared to this one. And it refers to June and July months that predominate in this cluster. We just did recently some new experiences trying to tune the weights of the comb distance. In fact, we could tune them so that the silhouette indices improved in all these examples. So in this application, we obtain improved silhouette indices. And what we also found out in this approach with tuned weights is that the structure that emerges from this more heterogeneous cluster is slightly different, which could be interesting to further explore in the future. So some discussion and perspectives. So we used these experiments conducted on the UCR data sets, the time series, And you used Uberty Index as a measure of performance that provides more informative analysis than simple accuracy, as we saw before. The complexity invariant distance was not used in previous studies, so it was used in our study and it proved to be very competitive. And as to our proposed measure, we think it shows very promising results. In fact, we are very motivated by the application referring to the electricity market prices. And one thing we can conclude from the experiments conducted is that a good trade-off performance between performance and computation time is obtained when compared to the alternative distances which were considered. And referring to applications, the combination we think achieved good results. So clustering time series of day-ahead electricity market prices in European regions, we could obtain clusters that reflect not only the different prices patterns, but they uncover the reason why they are different, and that is also based in the interconnection, which is related with geographic proximity. And daily patterns of electricity consumption in Portugal, the clusters obtained, they capture general differences between the electricity consumption of working and or non-working days. Also, it captured differences between the seasons. And in addition, we could find several different patterns of consumption that could not be guessed by the experts. They are related namely with temperature, for example. In future experiments, we want to extend the analysis, the competitive analysis of COMB to all UCR datasets. That's a challenge because we have datasets that can take 3 days to run, and these are the ones that we already were able to achieve results for. And to include COMB with different weights, of course, it is something we are dealing now, just because we found, for instance, in the herring worst COMB example that transformed to be the best one after this tuning of the weights, and also in our last application. And so we can maybe in the future present some results concerning this tuning of weights in COMB. Future software implementations could be very useful for the computation, since the computational cost for the comparison of UCR datasets is very high. And at the moment, we also have an application where the approach we proposed here, based on COMB and clustering with k-medoids, was used and integrated in a clustering-based similar pattern forecasting algorithm that was recently proposed. So thank you all for your attention.